of the edges outgoing from source vertex. That is the flow of a network, and it comes out to be 2 in this case. And net flow across the cart is defined as this, which is also coming out to be 2, and we will now see these two are same. Okay, so save image, save PDF. Let me check once whether it is saved or not properly. It is very, very important. Right, it's fine. Okay, so now we can flow network part, sir. Okay, flow network, you understood, we have covered the flow network in the last class. What is a flow? So in a given network, the flow means the sum of all the flows of edges outgoing from the source vertex. So source vertex outgoing edges from source is this one, S to A and S to B, right? So if I write here, so equal to flow of S to A plus flow of S to B, and that is equal to 2. 1 plus 1 equal to 2. So this is the meaning of flow network, how we compute the flow network. Or it is also equal to the sum up of all the flows of all the edges incoming to the sink vertex T. So it is also equal to f of C comma T plus f of E comma T, E comma T, and their flows are 2 and 0. So 2 plus 0 equal to 2. And you know, from the conservation of the flow rule, we have this is true, that the flows sum up of all the flows outgoing from source must be equal to the flows of all the edges incoming to the sink, that is 2 2. And you know, this is entirely different definition of flow network, and this is entirely different definition of flow across the cart. See, f of SB minus BC, and it is only SA plus SB. So these two are entirely different definitions, but still we have seen that this flow network of this flow of this overall network becomes equal to eventually the net flow across this cut. And we will see next that these two will be very, very true to be equal to each other, okay, through a lemma. Because S prime is a ordered cart set. So this is the definition of S comma S prime. The cart consists of edges with one endpoint in S and the other in S prime. So in BC edge, the first vertex B, it's an order. B comma C is not same as no, C comma B. So their orders are different. So if you consider BCH, B has to be present in capital S, but B is not present in capital S. B is present in S prime. That's why BC can't be an edge in S prime, S comma S prime cut. Okay. Any other question? So let's try to save this. Right, now it's fine. So we can delete that. Okay, so coming to next one, see, we want to erase this overall portion. We want to go to a lemma now. Okay. Very advanced topic this is, and very important. Okay. Lemma 1 says that let F be a flow of a flow network, okay, T with source S and sink T, okay, and let S comma S bar be an SD card, okay, SD card, then the net flow across the card S comma S prime is uh, follows uh, the flow of the network, which is denoted by mod of F. So F, which is F of S comma S prime. Okay, so this let's say this is so let F be a flow of a flow network G with this, and the net flow across the cart is F of S comma S prime. These two are equal to each other, which we have seen here. The flow network mod of F is 2, and the net flow across the cart F of S comma S prime is equal to 2. So these two are same, and that is well true because it's a lemma 1. Okay, fine. So just let us try to prove this. So means summation of flow of all the edges where E is of, not capital S, it's a small s. Okay, so this is capital S, the set of all vertices. This capital S and small s, please try to uh, please try to not to be confused. Okay, so this is E out of small s. Okay, this is E out of small s. Next, in the next line, what we can write equals to the summation over, okay, so this is means flow of S to A, S comma A plus flow of S comma B. That is the meaning of this line. So flow of all edges, the edges which are coming out of S source. Okay, I just want to mention here, S is source vertex. Here, in the next line, what we can write, that is summation of all flow of edges, the edges which are coming out of the capital S, and minus the summation over flow of all edges which are into, oh sorry, intermediate vertex V. Okay, so E into V, and let's say this is right. Okay, So we put a bracket over here. Sorry. Okay, so let me write a bracket here and here. This overall expression, so this bracket start, this bracket close. So this overall should be inside a summation. Okay, inside a summation. Okay, so this is that bracket. So it is V belongs to capital S. Okay, so this is true. So the summation for all the vertices belong to capital S means S, A and C. So all these three vertices. So for all these three vertices, if I take an intermediate vertex V belonging to this capital S, so you sum up all the flow of edges coming out of V and you sum up all the flow of edges going towards V and find the difference. Okay, and that is equivalent to this summation. Okay, so in the next line we can write that. So this is basically summation over f of E, where E out of S and then some minus summation over f of E, where E is into S. Okay, and in the next line, so this is the definition of f of S bar, so hence proved. Okay, so we have proved the to f of S comma. And let take an illustration. For this example, so this is very important. Illustration C. So we have mod f equal to flow of S comma A plus flow of S comma B. That is the definition of flow of this network. Okay, and then you see flow of S comma A B C. So as per the second line, this line. Okay, you see how we can write. So this is saying that you sum up all the flows. You sum up all the flows from outgoing from S. So you consider all the vertices A and C separately. So first we consider the vertex S and find all the edges outgoing or incoming, outgoing from S or incoming to S. And we have seen that two edges which are outgoing from S, SA and SB. So sum up their flows, f of S comma A plus f of S comma B, right? And there is no incoming edge towards S. So vertex S is completed. Next consider vertex A. So one edge is outgoing from A So sum of that f of a comma c, and then you then no other outgoing edge from a, and you find one edge which is incoming to small a, SA. So that means it has to be subtracted, S comma A. Okay. So you add up all the outgoing edges and subtract all the flows of incoming edges towards a vertex. So while considering vertex A, we have one incoming edge, one outgoing edge. So plus f of AC but minus f of S comma A. Okay. So A is completed. Next you consider vertex C. We have one outgoing edge and two incoming edges. So plus f of c comma t, which is the outgoing edge, but minus f of a comma c, okay, and minus f of b comma c. Okay, these two are incoming edges. And why this line is equal to this line? To understand that line, we are illustrating this. And these two lines will be this can be proved actually. We are not proving this line, we are just illustrating it to make you understand. And it can be, if you want to prove this, apply the flow conservation rule. Okay, flow conservation rule, then you can automatically prove this. Okay, so f of a comma c and b comma c, and let's see. So S comma A and S comma A cancelled out, and A comma C minus A comma C cancelled out, and what we have, f of S comma B plus f of C comma T, and minus these two are grouped together, so it is looking like a set. So these are grouped together, and then f of B comma C. Okay, so you just observe this is the summation over all the flows of edges of which the first vertex belongs to capital set. See, so small s, small c are belonging to capital set S and capital S, and second vertex B T, these are belonging to S prime. That means these are edges in the cut. See, SB and CT, SB and CT. So these are flow of edges belonging to the cut S comma S prime. Okay, that means these are the edges which are coming out of the capital S. SB is coming out of capital S, CT is coming out of capital S, and this is the edge BC which is going into the vertex set capital S. So this is the first summation in this equation, in this definition, and this is the second summation in this definition. So this is basically nothing but f of S comma S prime. Hence we have proved that, illustrated and proved that, verified that the flow of the network is equal to the flow of S comma S prime. So this is the proof and the illustration of the first lemma. Okay. So next we go for the second lemma. Sorry, এটাকে একটু সরিয়ে দিই। এটা একটা পিকচার তোলা যাক। Now we can erase. So we have another lemma, lemma 2. These lemmas are very important while solving problem. Okay. So lemma 2. So let f be any flow in a network G and S comma S prime S prime be any ST card, then we have a relation mod f is less than or equal to the capacity of that cart, ST cart, which is true. Okay. So we know that flow is equal to the summation over all Fe, summation over all E out of S, summation of Fe for all E out of S. Okay, and then minus summation over Fe, summation of Fe over E into S. This is um, okay. So next we have here so the first quantity minus second quantity. So obviously this overall expression is less than or equal to the first quantity, right? So we can write less than or equal to the summation over f of E for all E out of S. Okay. So in the next line we can write that. So a flow of an edge is always less than or equal to the capacity of that edge. Remember, that means the summation will be also less than or equal to, summation will be also less than or equal to the summation over C of those edges which are coming out of S. Okay, because we know we have the capacity rule. This is from the capacity rule. Because any flow of an edge is less than or equal to C of that edge. So this is the capacity rule. Okay, so already time is up. Okay, fine. So we will wrap up shortly. Right. Okay. Right. So next, what we have. So this is in the next line. What we can write, that is, mod f is less than or equal to summation over CE out of S. Okay. So the edges which are coming out of S are the edges belonging to the cut, and the summation of the capacities of the edges in cut is actually the cut capacity, so which is equal to capital C of S comma S prime. That means the mod f is less than or equal to the capacity of S comma S prime. So hence mod f is less than or equal to comma S prime. Okay. This is your second lemma. Okay, proved. And we now consider the third lemma. Can you repeat the last lines? Okay. So So up to this you have understood summation over CE for all E out of S. This is fine. Now what are the CE which are coming out of S? These are the, in this example, the edges which are coming out of S to B, CT. Those edges are nothing but edges in the cut. So these edges which we are talking about, the edges which are coming out of S is nothing but the cut edges. Their capacities are CE. So if you want to sum up the capacities of all those edges in the cut, the sum will give you the cut capacity. That is the definition of cut capacity. Okay. So cut capacity is defined as the summation of all those capacities of edges which are belonging to the cut. That's why this summation is equal to capital C of S comma S prime. So hence mod F less than equal to capital C of S comma S prime. And I just want to conclude with the third lemma. Okay. Third lemma is very simple, easy. Lemma 3 is let F be any flow in G, and actually mod F, we may write F simply, but more specifically we want to write mod F S comma S prime be any ST cut if mod F is equal to the capacity of, this is directly, this can be proved actually, very easy to prove. If this is true, if mod F is equal to the capacity of the cut, ST cut, must be the maximum flow of the cut S comma S prime cut. It's a very important thing. Maximum flow of the cut and S prime will be the minimum. Okay, so here we have simultaneously a situation where a cut can be both maximum flow cut and minimum cut. Okay, so if I achieve this condition, if we can find a flow which is equal to the capacity of the cut, then we can infer that that cut is a max flow mean cut. Okay, together it's max flow mean cut. So it's already 10:49. So I think you have some next theory class. So please tell me what is the mode of the class. Can I extend to 2-3 minutes? 2-3 minutes to wrap up. No problem. Okay. Just see. So because I just want to, okay. Because now I just want to, tell you about max flow mean cut theorem. What is the max flow mean cut theorem? If is a flow, may not be RA. Right. So if F is a flow in a flow network, okay, G with source S and sink T, okay, then the following are equivalent. So number one is F is a maximum flow residual network GF, the residual network GF contains no augmenting path. Okay, and the last statement is, third statement is, mod f is equal to capital C of S comma S prime, which is the third lemma. Okay, some cut S comma S prime. Okay, okay, so delete the, okay, let me save this. Let me save this once. কোথায় গেল এটা, কি হলো কেসটা? So let me save. Okay, wait. Okay, so it is not coming like that. Okay, so let me okay, delete this. For some cut S. Concept is very important, we can't miss actually, then it's fine. Okay, so it's fine now. So now we are about, we can zoom it, no issue. Okay, so this is the concept, this is the flow, very important theorem to understand with. So these are the three statements. Okay, so these are the three statements. So theorem is if f is a flow, what happened? Okay, so if f is a flow, if f is a flow in a flow network G with source S and sink T, then the followings are equivalent, following statements are equivalent. So f is a maximum flow in G, that means equivalently the residual network GF contains no augmenting path. Okay, and if, or we can say that the flow is equal to C of S comma S prime for some cut S comma S prime. Okay, so this is very true, this is a very very important theorem, max flow mean cut theorem. Okay, so we will apply this theorem to solve some example or solve some problems. So I will give you some quiz and one illustration through which you can understand the theorem better. Okay, so with this we can wrap up the session. If you have any question, please ask me. Okay, so I shall I shall provide a quiz. Try to solve yourself. Okay. And please circulate the recordings or snapshots. Sir, point number 2 once more. Oh, point number 2 is nothing. The residual network GF will not contain any augmenting path. So if F is the maximum flow in G, then I can also say that the residual network of GF will not contain any other augmenting path available. And we can also say that that flow will be capital C of S comma S prime for some cart S comma S prime. So these three statements are equivalent. Okay. Yes, in Moodle. So please try to solve the quizzes on yourself. Otherwise, you ask me queries. Okay. Okay. So anything else? Okay. No issue. So I hope you know the talk, you understand the concept of lemma 3. Oh, lemma 3 is very simple. Lemma 3. If this is immediately following from lemma 2.
স্যার স্যার
Yes.
স্যার একটুখানি জুম করা যাবে স্যার, দেখতে পাচ্ছি না।
Zoom এখানে okay.
হ্যাঁ এবার ঠিক আছে স্যার।
Right. So
হ্যাঁ হ্যাঁ
let f be any flow in G and S comma S prime be any ST card, and if the flow f is equal to C of S comma F prime. See, so this is directly can be inferred from this lower bound, or sorry, upper bound. Okay, f is less than or equal to C comma S comma S prime. That means the maximum value of f must be C of S comma S prime. So that if f is C of S comma S prime, then that is the maximum flow. That means f must be the maximum flow of S comma S prime, right? And if f is maximum flow, we can also say that that cart will be a minimum cart. So max flow and mean cut together we can combine here. Okay. Anything else?
না স্যার।
Okay. So thank you.
ওকে স্যার, থ্যাংক ইউ।